So let's try the problem. So here we're going to have a supersonic flow that is deflected or expanded around a sharp corner. Sharp is a key word here because we're dealing with these things using that sharp definition. It can be not sharp, but then our expansion fan isn't really much of a fan. We have to think about things slightly differently. So this will be 15 degrees right here. And there is the ground. So the flow before this expansion fan, I always draw expansion fans as little V's, is going to be a Mach 1 is equal to 1.5. And my pressure 1 is equal to 1 atmosphere, pretty normal. And my temperature is going to be equal to 288 Kelvin. And so what I'm trying to figure out is everything else. So what is M2? What is T2, P2, T02, and P02? Okay? What are all of these things? What be they? So we're going to go through this just as we would. So for any expansion fan problem, for all of them, the first step is going to be calculate the Prandtl-Meyer function. Now you can, if you want to, plug it into that horrible equation from earlier. Don't. That's a bad idea. Unless you've done it in Excel and you've already set it up and you've practiced it and you made sure it's actually working, then it's a great idea. But don't do it more than once in your calculator or Excel. Make the equation, make the spreadsheet, whatever you want, make the script, and then just keep on running it once you've proven that it worked properly. So we're going to calculate nu. How do we do that? Well, we're going to go to the tables. Why? Because tables are awesome. Why not use the tables, everybody? Give tables a chance. So here I am in a textbook, McGraw-Hill Connect. I'm going to go to Appendix C this time. Appendix B was for normal shocks. Appendix A is for isentropic flow. Appendix C is for the Prandtl-Meyer function, as well as the Mach angle. Don't deal with that as much, but it's sometimes important. Okay, so here it is. So we have a Mach of 1.5 to begin with. So I'm going to go down to here. I see 1.5 right here on this line. And so my value, my Prandtl-Meyer function is going to be 11.91. That is in degrees, but don't worry about the angle too much. So 11.91. This is also the point where you should probably be asking, well, what is a Prandtl-Meyer function? Good question. Just don't ask that. It has degrees. We can add the angles to it, but it is under no circumstances the same as the Mach angle. Like this is mu1. That is mu2. Okay? That you can also find from your Prandtl-Meyer function tables if you want to get an idea of where this expansion fan begins and ends physically. Just like you might want to know. But that is not what nu1 is. Okay? That is just a value we're using to do these calculations. And it's built up just trying to figure out how a flow would change over an infinitely small Mach wave. Your book has a great derivation for it. I'm not going to worry about it too much. So we went to the Appendix C. And for Mach 1 is equal to 1.5, we found that nu1 is equal to 11.91 degrees. Great, we have that. Then we know we have to calculate nu2, which is incredibly easy because that's simply nu1 plus the deflection angle. Is it always that? Yes, yes it is. It's really that simple. So I have a deflection angle of 15 degrees, so I have 11.91 plus 15 degrees. What does that come out to be? That comes out to be 26.91 degrees. And that is equal to nu2. Okay, so far everything's going pretty well. So now that I've done that, I'm going to go back to the tables and calculate what Mach 2 is. My Mach number after the wave is going to be. And so that's going to be in Appendix C once more. So let's hop back there and look for 26.91. As a note, I'm just going to find what is closest to this and be happy with it. So I'm looking and I see, it's about Mach 2 right here. Mach 2, 26.38, that's pretty close, pretty close. It's a little bit above it, it's probably like Mach 2.01, but we're gonna call it good. So my Mach number after the expansion fan is 2. So from Appendix C, using that nu 2 is equal to 26.91, I find that my Mach 2 is going to be equal to 2.0. Okay, so this is great. I have my Mach number before the expansion fan, I have my Mach number after the expansion fan, but I still have to calculate all that other stuff. The great thing is, I don't have to plug it into any equations, I don't have to do any hard calculations. It's now just go to the appendices and find the information you need. So we're going to now calculate everything else. And how we're going to do that, we're going to go to Appendix A. So Appendix A has all that information. Remember that Appendix A is my isentropic flow table. So since expansion fans are isentropic, we can go through an isentropic flow. It works out really nicely. So we're going to find a lot of information for Mach 1, which is equal to 1.5. We're also going to find that same information for Mach 2, which is equal to 2.0. What we're looking for P01 over P1, T01 over T1. We also want P02 over P2, and T02 over T2. We need all of that information, all of it. If we get it all, we got it all. So let's go find it from the table. So back over to this is Appendix A, Appendix C. Now I'm in Appendix B, and finally Appendix A. Be very careful. Remember that it's always times 0, and then it's times a factor of 1. So times 10. So that'd be 1.5 is right here. This line right here. This first column is the pressure ratio. The third column is the temperature ratio. I'm going to check that because I doubt myself sometimes. I was right. Okay. It's nice when you're right, but okay. So what I get then is that my P01 over P1 is 3.671, and my T01 over T1 is 1.45. If I go down a little bit, I can find it for Mach 2. Can't quite fit it on the same page. Oh, I can. And so I get that my P02 over P2 is 7.824, right there at the bottom, and my T02 over T2 is 1.8. Now I'm going to write down all these numbers for you, so if you're, I'm going to jump back there, but I will give you all the numbers so you'll see them. I just wanted to show you where they came from. Don't take my word for it. Make sure that you know where the stuff comes from. So I get 3.671 for that, and 1.45. And then I get 7.824 for that one, and then I get 1.8 right there. So I have all my values, and using that, I can then keep moving forward and calculate all the properties that I need for this expansion fan. So what are those properties? Well, the first one we're going to get is P02 and T02. Why? Because those are the ones that are ridiculously easy. P02 and T02, since it is isentropic, are equal to P01 and T01. Happy days. And what is P01 and T01 equal to? Well, they're equal to P1 times P01 over P1, and that's equal to T1 times T01 over T1. So, not bad. I think we can solve this. Hopefully we can. I'm just believing. Okay, I'm just believing. So we'll plug all the values in. We had 1 atmosphere. And then I have P0 1 over P1 of 3.671. So it'll be equal to 3.671 atmospheres. That looks good. I like it. Okay. And T02 is equal to T01. It's equal to T1 times T01 over T1. So my T1 was equal to 288 Kelvin. And T01 over T1 was equal to 1.45. So what do I get then? I get 417.6 Kelvin. Okay, that's looking good. I've got my stagnation pressure and temperature. And now I'm going to find out what P2 and T2 are. Okay, so we're going to write this out as we've done in the past. So P2 would be equal to P2 times, let's see here. Not going to do it by that way, sorry. P2 over P02, there we go. Times P02 over P01 times P01 over P1 times P1. Woo! That's a lot of stuff there, isn't it? A lot of stuff to plug in. But it's not nearly as bad as you think it is, because remember P02 and P01 are the same, so that is just 1 right there. And we have the exact same scenario for the total temperature. So I find the static temperature. So T2 over T02, T02 over T01, and then T01 over T1, and then finally T1. Goodness. But that one right there is still 1, so we really don't have all that much to do. Now, when you're doing this, be very, very careful, because remember that when you're getting the values from the appendices, it's always the not on top of the static. So the stagnation on top of the static. And right here, I do not have that. I have the static on top of the stagnation. I need to invert it. So just make sure you're seeing that so you don't make any mistakes. So this would be equal to 1 over 7.824, that's me inverting it, times P01 over P1, which is 3.671, times 1 atmosphere. And if I plug that into my calculator, what do I get? I get 0.469 atmospheres, so it has halved after going through this. Does that make sense? Yes, because I would expect an expansion fan to drop the pressure. Okay, now let's try the second one. So I've got T2 over T02, so that's the inverse. So I have 1 over 1.8 times 1.45 times 288 Kelvin. And that comes out to be equal to 232 Kelvin. So the pressure dropped and the temperature dropped, which is what I expect. Sorry, the static pressure and the temperature both dropped, and that is what I expect. So I have everything here. I've got my final Mach number, got that earlier. I have all the values, and we are done. This is it.